Modern life is built on a single element more than any other: carbon. The fuels that move vehicles, the plastics that shape products, the medicines that save lives, and even the molecules inside your body all share one thing in common: they are carbon based. Understanding why carbon dominates chemistry explains how organic chemistry quietly built the modern world. This is the Learning Studio, where chemistry is explained as the foundation of real systems, not just laboratory reactions. And after seeing how chemistry became a tool for building civilization, the next logical step is to understand the branch of chemistry responsible for creating most of the materials and molecules we depend on every day. Most people think organic chemistry is simply the chemistry of living things, but in reality, it is the chemistry of carbon and its unmatched ability to form complex structures. For example, gasoline, plastics, synthetic fabrics, pharmaceuticals, and food additives may come from very different industries, yet they are all organic compounds. Their diversity comes from carbon's ability to bond with itself and other elements in stable, flexible ways. At the atomic level, carbon's power comes from its bonding behavior. Carbon has 4 valence electrons, allowing it to form 4 strong covalent bonds at once. This lets carbon atoms link into long chains, branching networks, and ring structures, creating an almost infinite variety of molecules. No other element combines stability and versatility at this scale, which is why organic chemistry became the backbone of modern materials and medicine. This structural logic was clarified in the 19th century by scientists like Auguste Kekulé, who proposed that carbon atoms bond in specific patterns and form ring structures. His work transformed organic chemistry from a collection of reactions into a science of molecular architecture, making it possible to predict and design new compounds instead of discovering them by accident. Once carbon's bonding rules were understood, chemistry shifted from observation to invention. Chemists learned how to synthesize dyes, fuels, polymers, pharmaceuticals, and agricultural chemicals by assembling carbon frameworks atom by atom. This ability fueled industrial growth, improved medical treatment, increased food production, and reshaped global economies. Organic chemistry also explains life itself. Proteins, carbohydrates, fats, and nucleic acids are all organic molecules whose functions depend on their carbon-based structures. The same principles that allow chemists to design plastics and drugs also explain how enzymes work, how DNA stores information, and how cells convert food into energy. Today, organic chemistry continues to evolve. It underpins green chemistry, renewable fuels, biodegradable materials, and modern drug discovery. Even AI-driven chemical design relies heavily on organic chemistry rules to predict molecular behavior and synthesize new compounds faster than ever before. And once we understand how carbon-based molecules shape fuels, medicines, and materials, the next question naturally follows. If organic molecules can be linked into long chains, then how did this ability lead to plastics, rubbers, and synthetic materials that reshaped civilization itself? That question takes us directly into the next episode, where we explore polymers and plastics, the materials that changed the modern world.